Thanks so much. Is this thing on? It's working? Cool. Wow, I can't even hear any echo up here. It's kind of funny how the only constant problem in computer science is enabling an external screen, no matter, like, I bet in 10 years we'll have somebody on Mars, but we can't, like, plug this thing in or, like, or do that. Okay, yeah, anyways, yeah, I'm Mathias. I'm from Copenhagen. I'm going to talk to you about a new thing I've been working on the last couple of weeks called Hyperdrive. It's actually an iteration on a thing I presented last time I was here. So there's a good continuity in that. I work on this project called the DAT project, and that's how I get funding to work on all these things. The Hyperdrive is also going to be part of this. It's a open source peer-to-peer data sharing tool. And if you're interested, come find me afterwards. I got stickers also. It's pretty cool. Sticker. So here's a fun fact I dug up while researching this talk. We're a 3-person team, all full time, and together we published more than 750 modules on NPM. The reason I have this on here is because I published most of everybody, so it's cool bragging, right? There's around 200,000 modules in NPM now, so it's around 0.5% of NPM. So if you use more than 200 modules, there's a pretty good chance you use some of our stuff.
So in what time frame?
This thing?
Yes.
That's a good question, actually. I don't know how to get that out of NPM, but this is like right now. I've been working with the other guys for a year now, so it's around that. Year and a half.
Publish a module a day.
Yeah, something like that. In reality, it's more like 10 modules in one day, and then I'll take a break, but on average, yeah. So yeah, you can probably describe most of my projects with this sentence, but I'm going to put it here anyway. So the Hyperdrive is a peer-to-peer file sharing network that's all written in JavaScript, and it's built for the browser and for Node.js first class. And we'll get back to that in a little bit. But similar to BitTorrent, it's basically evolving around doing this thing where you want to download some files off the internet, but you just don't want to download it from one person. You want to download it from everybody who has that file, right? And BitTorrent is kind of the de facto standard of doing that now. And if you've been following my work, I've been doing a lot of stuff with BitTorrent. So it's like a natural progression for me, going from something like BitTorrent and trying to tweak the things I don't like about BitTorrent into a new, better thing. So these are the 3 main goals of my project. It's about smart diffing. So what I mean by that is if you publish a file and you then update that file and publish again, you want to have a smart client that'll only download like the diff if you had the old file. This is something BitTorrent doesn't do, and it's really annoying if you use it for something like datasets, which I want to do. Deduplication. If you ever downloaded a file from somebody and somebody else shares the same file, you don't want to download it again. This is also something that BitTorrent doesn't support. Simplicity modularity. This is actually something that BitTorrent is really, really good at. I wanted it to be really, really simple, meaning that somebody who's experienced in building distributed systems or like general network tools can sit down in a weekend and implement a client that's somewhat spec compliant. It has to be that simple, so no like super fancy new stuff that's crazy difficult. There is some crazy difficult stuff in there, but it's not that bad. Modularity in the sense that this should be built with as many small components as possible, not one big thing that you can't really use. So smart diffing, what do I mean by that? So yeah, I always said this, but basically diffing is a way of, if you have a file, it's basically a way of dividing that file into a bunch of chunks, and chunks is just like an arbitrary range of bytes. And you want to be smart about dividing this file into chunks in the sense that if you update the file, you want as few chunks as possible to change, right? So then we'll have a small diff. So a really, really good example of some tool that's really, really good at this is Git. You probably all know Git. I hope you do. So what Git does is that if you have some source code, it'll just scan through that source code and until it finds a new line. And every time it finds a new line, it'll use that as a new chunk. And this is a really good way of dealing with source code because new lines are kind of like a natural delimiter in source code, right? We don't have that long lines, so if we change something, should change that to a German word, I guess. I presented this in France also. If you change something, a line, you'll only change a very little part of the file, right? So if you change this one line, 3/4 of the files are unchanged. So it's a really good strategy for source code. There's only one problem, it only works for text files. So if you ever try to add a binary file into Git, you've probably figured out that it doesn't really work because it'll just look through the binary file for new lines, which is kind of like a bad idea. So you'll end up downloading and downloading and downloading the same file again. And I've had a few jobs in big corporate companies where somebody always adds a zip file to a Git repository. And now, congratulations, you have 100 megabytes you don't ever get rid of in your history. And then somebody updates it, and now you have 200 megabytes in your history you'll never get rid of, and then you start breaking Git. So that sucks a lot. So how can we fix that? So I read this paper that's really old, actually, about something called Rabin fingerprinting. And it's a really novel way of solving this. It's also called content-defined chunking as a more generic term. And I'm going to try to quickly explain what that is. So basically, it's a way, and it's like a very novel mathematical way of doing this that I honestly don't really understand, but it works. Where you basically have a function that scans through a file, and it will define chunks based on the content it finds using a sliding hash. So basically, you scan through a file, and it'll hash a range of bytes all the time until it finds like a natural delimiter in that hash, because hashes are uniform. There'll always be a natural delimiter if your file has a natural delimiter. I know it's a lot to take in, so don't worry about it. It basically ends up dividing your file into a bunch of chunks that are not necessarily the same size, but they'll be the same chunks if it's the same content. So here's an example where, let's say it divided a file into 5 chunks, and you can kind of configure the parameters of this algorithm to produce the chunk size you want. So something like 10 or 16K is a good chunk size. And let's say we insert something in the middle of the file. Since the content on both the left side and the right side hasn't changed, if you run the Rabin fingerprinter again, it guarantees that it will find the same chunks on the left and right side. But in the middle, there's going to be new chunks. But at worst case, we only modify that one chunk we're overriding, all the chunks we're overriding, and the neighboring chunks. So it's a really good diffing strategy. So me and a friend of mine implemented this. It's called Rabin on NPM. I'm pretty surprised we could get that name, actually, but we could. And when I say implemented, I mean we found a C implementation and basically copied it and tried it, and it worked. And again, I'm not sure how it works, but it does. But I have an implementation demo of it here, which is pretty cool. So just going to try to show that. So let's say you have a CSV file, for example. It'll basically produce this thing, which is basically just a bunch of hashes for every chunk it finds in the file. So this makes no sense to you, and that's all right. But if I now open this CSV file in an editor, and I go down to a random place in the file, and I insert hello in the middle of it, and save it, and run it again. Actually, I should save it as a copy, because otherwise we have no way of verifying that I'm correct. cp.copy. Oops, that's fine. Cops. Nice. That's why you have the German keyboard, so you randomly insert fun stuff into everything. So I'm editing this one of the files, hello world, saving it. So now if I run the Rabin fingerprinter again and run it for the other file, cups, we'll notice here that the last hash is the same as the previous last hash, even though I inserted something in the middle of it. Both of them are E40 something, and this one is also E40 something. So if we use compare, it'll tell us it's not the same file. They actually differ around this offset. So if I just, that's around 1 million. So if I find this offset in the file, it's probably going to be here. So let me just quickly check. 42 something, 90, 98. See. In my terminal, I can just search for it, but I don't know how to do it in this terminal. You do? Oh, there we go. It's here. See, so there's one in the old file that's C39, and there should be one in this file also. That's C39. But the next one in the new file, that's where I inserted the chunk, is 42 something, 42 E1. And if I go up and find 39 in this file, who's better at me? Oh, there's still this one. Okay, so this one is bound to be different. This is the same one, so 93 OB.
Okay, this point is not the 42.
Oh, this is also the same. It's got to be this one then. 9943.
But you could just capture both outputs and make a diff of those.
Ah, good point. I can just run diff here, can't I? That's way easier than what I was doing. Then I need to find the redirect character. There we go. Diff 1. Man, that's way better than what I was doing. Diff 1, diff 2. Wait. Oh, because they all shifted?
Make a dash C4 or something.
Wait, what? Dash. Oh, dash C.
Like then it's just the context of
like that?
the lines.
Like that? Dash C4?
Yeah, I think it's a capital C, sorry. No, not working.
Anyway, so it tells us that there is a difference around here in the middle, so you just have to believe me. You can try this at home.
You can use the Vim diff.
Yeah, I don't know how to do that. But anyways, it'll just modify that one chunk in the middle, which is pretty cool. And it works even for binary files, so even if you show some scrambled data in the middle of a file, it'll be fine. So that's how we do diffing. Deduplication. So like I said, it's about only download and store a given chunk once. So if you ever download a piece of a file and you want to get the same chunk again, don't download it again, just get it from cache. So for example, before when I ran npm install Rabin twice and it downloaded something off the internet twice, that's really annoying. It should just be the same thing. So here's a really classic example. It's just sharing two copies of the same file. So if you have a file that looks like this, myfile.data, .data is the most neutral extension I can come up with that nobody can correlate to any sort of piracy or anything. So it's just data. And you run it through the chunker, and it gives you these 4 chunks: chunk 1, chunk 2, chunk 3.4. If you now use this simple technique where you just hash every chunk and store it as a pointer for the file, so the hash of the content is actually a pointer to the content. It's called content addressability. It gives us this really nice property that if you copy the file and you apply the same technique, you'll get the same hashes out. So if you're basically just searching for these hashes, you'll find out that you already had them. So this is really cool. Also, if you just share the hashes up front, then you won't need to re-download anything, because you can just, if you download this one file once, you get all the hashes, and then you try to download the same file again. If you get all the hashes first, you'll just notice in your cache that you already had these hashes, right? So that's really clever. And even if the files are not completely the same, even if only half of them are the same, or in my CSV file that I just tried to show you before, where most of it was the same as I showed by not finding the diff, a lot of the hash will be the same. So we only end up downloading that small diff. So that's really cool. And you can even apply recursion to this technique where instead of getting this list of hashes, you just hash every other hash, and then you get half as many get half as many hashes, and apply it again, and then apply it again until you only have one hash. And this hash kind of globally identifies your entire file. And we also call this Merkle trees. It's a pretty good joke, if I must say. So the cool thing about it is that the top hash, basically the hash on the most left side, deduplicates the entire file. So if somebody sends you that hash and you have that, then you know that you have the entire file. If you don't have that, you ask for the two next hashes, and you'll just check, do you have either one? And if you have the top one in the middle, then you'll know you have half the file, so you don't need to download that. And you'll continuously go down this path, and you'll only end up getting the diff. So that's a really old, really proven technique for only syncing a small diff of a file. We need to watch that again. That's pretty good.
Can you go back to Angela? Yes.
I guess I spelled this wrong, right? Oh, never mind. So I put that on NPM. It's called Merkle tree stream. It's basically just a stream you can pipe things from. It'll produce a Merkle tree for you. And I won't bore you with a demo of that because it's pretty boring, but it's super useful. So that's end of the boring part. I'm going to try to demo the system now on a computer I haven't used before. So that's bound to be interesting. So I made a static build of this on the internet and it's hosted on GitHub pages. Oops. It's all right. I misspelled it. Everything is fine. Hyper. Oh, where's the Y? Why do you switch the Y on this keyboard? Cool. So you can also be impressed by my really good front-end skills. So yeah. So basically, there's this website, and it tells you can drag and drop files to share them. So I'm going to try to do that. So I have a file here that's empty. So if we just open this up and write hello world in it, I can now drag and drop this file onto the page. And what I'll do is it'll generate this Merkle tree that I talked about by applying the Rabin chunker. This is all being done in the browser. There's no server-side component of this. And this hash up here that's really small that you probably can't see is actually the root hash of that Merkle tree. So what you can do is you can take this link and you can send it to your friend. So I'm just going to be my own friend because that's the best friend. And try to open it here. So let's try that again because that was really fast. So what will happen is these two browsers will find each other, and this should work over the internet also. In this case, it's using WebRTC, but it can actually run over any stream in Node, so it can run over TCP or a UDP stream. But the only thing we have in the browser is WebSockets and WebRTC. And to connect two browsers together without a server, you need WebRTC. And you can click this file, and you get the contents of the file. So we just probably use the most expensive way ever to distribute Hello World, because we generated a Merkle tree and used all kinds of machinery to transfer that. But it works, so that's kind of cool. And the more people who join this swarm, shared link, they're all sharing it with each other. It's like a swarm of people, so it's not just one-to-one. They all help sharing it. So hopefully, let's try this. If I open it again, you can probably see now that they're all connected to peers and replicating this. So that's cool. So let's try to share something more interesting. So it works with multiple files also, so I can share a picture of myself. It's always good. I'll take the CSV file that we played around with, and let's, for fun, just take the presentation also. So if you drag and drop these in, I'll make it will make a new Merkle tree. And I need to refresh this because it's a hash. and I can view the PDF inline here. So this is actually still syncing because it's more data. So it'll probably take a little bit longer to sync it. I don't know why it's not showing that. There we go. I just didn't click hard enough on this German mouse pad. It only responds to force, I guess. Oh, okay. Should not have done that one. And I can view pictures in here. And I can even view this PDF file. CSV file. So again, these are all pretty small files, so let's try to share something more big. So I have this one is a 100 megabyte CSV file. So if I drag and drop this in, generating that Merkle tree will take a bit longer in the browser because the browser is really slow at reading files for some reason. I don't know why. In Node, this takes a couple of seconds, but in the browser it takes more like 10 seconds. I guess they're not focusing on improving file I/O. So let's try to replicate this one. So actually, as soon as I click this, I'm able to see something, even though it's still syncing, because it can do random access syncs. So it's basically a stream of a CSV file here. So you can access this as soon as possible. You don't need to wait for anything to sync. It's all real time, even though it's all peer-to-peer at the same time. So that's really cool. And that's actually really useful for datasets, because there's a lot of datasets you can actually use without replicating the entire thing. But you can also use it for fun things like video. So I have this video here. I'm going to try to drag and drop that. Again, let's see the progress here. So remember, this is all running in the browser. There's no server-side component on this. So this is around 130 megabyte video. So it's not that big. That's just because I don't want to wait here for 10 seconds while it's doing the chunking, which we are doing anyway, but 20 seconds then. And again, this all works from Node also. So I could just have done this in Node. I don't want to run this on this machine because I don't have my setup here. But I can just share these files from Node instead, and it'll be way faster to chunk them and still view them in the browser. So this is local. I can click this file. This is local, and I can view it. So that's just normal. Hopefully I can view it. Yeah. But let's pause this. The cool thing is, if I share this now, it'll load a file, and it instantly load it. I can click it here, and it'll hopefully real-time stream the file in by only syncing the parts it needs to show the MP4 file. So even though it's still syncing, and it's all running in the browser, there's no server-side stuff or anything, you can skip it. And the video here runs a bit chunky, and that's because in the browser, when you have an external monitor attached, this video is really, really slow for some reason. It actually runs really, really good when I just run it on my laptop, so you just have to believe me on that. Actually, I might be able to. So I can skip into random parts of the movie here, and it'll prioritize that sync. And the way it's being done is it's actually passing the MP4 file from JavaScript in the browser, figuring out where their index is, syncing that index only using the Hyperdrive stuff, and then displaying it in the browser. So you can share videos with anybody without having to use a server. And they can just sync the parts they want. I actually think I can make this run a bit faster if I just apply this one weird trick. Yeah, so this is the log of all the chunks it's syncing right now. So let's just, so if I said, I think it's max in flight equals. So I might be able to make it run better by making it fetch slower, because it's the hashing is also taking its toll on the machine. Should probably do like that. So let's try that. So right now it's only being stored in memory, so every time I refresh it clears the cache, so it's actually re-replicating, but you can easily store it in the browser file system. I didn't really help that much. Let's see here. Oh, I think, Oh, it's because I made a new build just before this. Actually, okay, yeah, whatever, it's fine. So it's because so the toll of passing this in JavaScript right now is there's a couple of bottlenecks, and because it's syncing so fast here on this really good internet, it's actually syncing too fast for the browser to play it. So by artificially limiting the actual bandwidth we can get for peer-to-peer, I can make it play faster. But I don't have that API right now in the code. So we might be able to test that now. So actually you can see it now, because now it started downloading, and now it plays really smoothly, because now I can use the entire CPU to render it. But again, it's only because we have an external monitor, which you can try it at home. So yeah, play videos in the browser. I think that's it. Yeah, thank you. In theory, this should work with any kinds of content as long as you have a player for it in the browser. MP4 is just the most fun one because video is fun. But I tried to make MP3s work also, but actually MP3 is harder to pass than MP4s, which is kind of ironic. But yeah.
Other questions?
Yeah, sure.
Sorry, I think I missed that part, but how do peers find each other?
Oh, okay. So they actually use when you run it from Node, they use the BitTorrent DST. So BitTorrent has a huge DST that's massively distributed. In the browser, they need right now to use a tracker. You can actually just get a link from this. I haven't exposed it yet, but you can get a link. You can paste to a friend, and they can exchange it. But it needs a tracker, so I have a tracker running. But in theory, you could just have the Node clients run this tracker also to make it distributed. I have a friend who's working on a WebRTC DHT, but it's a pretty massive undertaking. So yeah.
I think you talked also the last time about it, right? I think it's on a video.
What thing, sorry?
This tracker BitTorrent thing.
Yeah, I think so. Yeah.
I think it was
Yeah. Any other questions? Sure.
Do you use web workers for the caching part? Or?
No, so it's all very naive right now. So there's a huge amount of ways I can optimize this. I actually didn't know it worked in the browser until 4 days ago, where I tried to browserify it and it worked. So I've only been using it from Node to share data sets. So you can definitely, there's a million ways to improve the performance of this right now. I'm definitely going to work on that. Also passing the MP4 files in a worker would be better. Cool.
Yeah, thank you very much.